the leaves of the tree. And we can put a layout, a Russell layout to the visualization, and also on the group. And here we can also put some interaction on the group or on the visualization. So when you put an interaction on an element, all the children elements take also the same interaction. So it means that here each node has the same interaction of the whole group 1, and exactly the same for group 2. So, and when we move one node to another group, it takes the other interaction, just because it belongs to the other group. That's it. So if you want to create a visualization, what you have to do. So as I said, the TL visualization is the root of the whole visualization, and it's a group as able to render itself. So as you can see here, we have a connector, so it's an abstract connector for the moment. There's only one concrete connector to Russell 2, but perhaps tomorrow there will be another one to block or something else, whatever, or Russell 3 or whatever. So we create a new visualization and we open it. And after you have some groups that define the structure of the visualization, and you can put a layout to place the inner elements. So here I added the group 1, and this superior sign is only a syntactic sugar. It's to express that you access to the group or you create it if it does not exist. So you can apply layout. So as I say to you, is a Russell layout. So here we are creating the group 1, so the one on the left. Okay. And after you have the nodes that are leaves of the visualization tree, and they contain the entity that they represent. So here we add the node from A to D, and we don't create the nodes manually. We just add them to a group, and the API do it for you. After you can put some action. So there's already a lot of actions that are available, but obviously if you want, it's open source, so you can add yours. And here we say that when we click on an element, the destination, it will move the element to the other group. And so no, it will change one element to another group, but it will be on click. And we will add an interaction also. So we will add the action through an interaction like this. And so here we add another interactions for the on mouse over, and that's it. It will be the group 1, and after we do exactly the same thing for the group 2, and that's it. So this one obviously is bigger, but because it is your own visualization, you have obviously to know the API, but we don't create the nodes. We just manipulate them. So, as a conclusion, Telescope is a model to represent visualization. It's built on top of Russell and lets the rendering to Russell. And if you get any question, I will try to answer, but I'm not sure. So here is the mail address of the guys that can answer to you.
a philosophy question, so maybe you can answer, but I'm going to answer anyway. So, first, I think it's a good idea to do stuff like this, because I use Wasal, and I know that you can do a lot of powerful things, but you have to know a lot before you can do a lot of powerful things. So to have this level of abstraction on top of it, I think it's really good. But now the philosophical question. If you make a level of abstraction on top of something, that means you make some things easy, and you make other things hard, difficult, impossible, I don't know what. So the philosophy behind is going to make this choice. So you have here visualizations, and there are visualizations to do what? This is my question. This is visualizations for the structure of software. This is visualizations for...
Currently, this telescope is already used for a lot of synaptic clients, so for software analysis, and they have made a lot of different visualization, yes, for software.
For the structure of software, for software execution, for what?
It's only static analysis, but you can have dynamic interaction with the visualization. And it's just because Moose is not very perfect for dynamic analysis that it is not used on with dynamic, but I'm quite sure that it can, if Moose supports dynamic analysis, telescope will be able to do it.
It's a matter of library, I have the impression. It's a library and you expand it depending on the... you have the framework and you feel it, you adapt it.
Yes, you can. The question is what's the philosophy behind it?
So the philosophy, this is that. So I can reply to that. Because we discussed... Okay. So the philosophy is that the visualization should become first class. And now we discussed with Alex what is the difference between the visualization and the builder. The builder, this is really something that emits things. You draw on the floor, and then when you draw on the floor, this is nice, but this is on the floor. And the visualization, this is something that builds the visualization, an object, and then after you said, oh, write it on the floor, and then you can live with that and do something else and rewrite on the floor, these kinds of things. And what we would like to see, this is, can we get more behavior of the visualization embedded into the logic of the visualization object, like open by default full, or open on a teeny screen, or, so that...
So I think my question ties in similar in that, do you find users who use Telescope, they use it as a stepping stone to learn the more in-depth topics of Rosal, or do they strictly stay in Telescope and they're completely comfortable with that?
So for the user, I will talk about me, because there are not, unfortunately, there are not a lot of telescope users because people don't know it. So that's why I defined it to present it today, because we need users, they need users, and contributors also. So for me, I already tried to use Wasal, and the problem for me in Wasal is that the order is really, really important. And I don't want to know the logic behind. It's not my fault. What I want is to put my data. And what I was doing when I was doing Wasal before Telescope is I was doing copy-paste. And I tried to change the thing. So it's a bit the same thing here. The idea is that I don't want to copy-paste. I just change the data by they develop an API in order to put the data.
I just want to say a comment. So also something that I feel is really valuable in Telescope, but maybe you didn't say it enough, I think, is the fact that Telescope comes with a set of visualization that are, that have been used with really big customers.
Yes.
And to visualize softwares. And the thing is, like, the visualization of that as telescope, they are indeed really well done and very well crafted. And if now I would like to do this visualization in pure RASAL, it would be difficult because RASAL, this kind of situation, I never seen that before, right? So the fact that, for example, you have the element on the left and you put it on the right, and then you have different kind of callbacks, reaction to events. This is not something that I've seen before, seeing telescope. And this interaction is important in telescope. So there are a number of very good ideas in telescope that probably percolate toward RASAL, and this will happen. This will happen, indeed.
Yeah.
Okay, last question.
Okay, so just very quickly, one more layer of abstraction we can go to is this interface is still great, and it allows users who don't have a lot of technical expertise to get visualizations, but it's still code.
Yes.
And a lot of the users we work with are not technical at all, they're business people. So what we found is to try and get this accessible to them. What we have to do is then add a user interface on top of that, which is driven from the metadata. So you look at the model, and you say to them, what do you want to choose from the model?
Yes, but I'm quite sure that it should not be difficult with telescope to put a graphical user interface in order to say this is the main entities or this is the connection to. It has not been done because currently when Synectic is working for its client, they do the visualization and it's not the client that do it, but
Yeah.
I'm sure that it should not be difficult with telescope.
I'm sure it's not, and I think this is a great step towards that.
Yes, yes.
So it's just the next level. Oh.
Thank you.
Thank you, Anne.
Ça c'est vous, en gros. Ça c'est merci. Vous êtes d'accord. Si tu veux encore autour de vous, allez-y, la question, on a 4 ans organisé, donc je vous trouve que vous savez faire. Prenez les décalages, si tu veux encore, venez, il y a la map, comment y aller. Juste ça. J'ai besoin de faire un truc.
Alrighty. Hello. Okay. So, my name is Andres. I write virtual machines and I work at Labware. And I haven't done formal paper presentations before, so hopefully this will go into round. So the idea I wanted to talk to you about is something that came up as a result of collaboration with Martin McClure over the years. I worked with Martin when I was at my previous employer for a number of years because Martin's employer, GemTalk, and now GemTalk and my previous employer were in a strategic collaboration with customers and whatnot, so we can touch over what I was over there, were performance considerations regarding memory management. Performance both in terms of reliability and also in terms of execution speed, and this is an idea that came out of that. But in order to tell you how it came to be, after I left my previous employer, I have to tell you a bit about the story about the parts that came together to make it happen, or to form the idea in the shape that you'll see. So I'm sure everybody knows about weak arrays. So there you go. You know, you have weak index slots in strong instance variables. And usually these things work, and as I'm sure you know, such that, well, here you have all this, weak array full of objects, and if the garbage collector detects, hey, there's no reference to that one, the garbage collector stamps that over with a tombstone. In the case of the VM I was working with, the small integer 0. And eventually that weak array gets queued for finalization, and eventually finalization mechanism sends the weak array the message mourn. Now, mind you, using 0 as tombstones is really great, because obviously why would you put an immediate object that will never be collected in a weak array? If you put it there, it will never be tombstone, because obviously an immediate object will never be collected. So it's great, because now obviously, well, look, it's an immediate object, so clearly it is a tombstone. So that's how weak arrays work, more or less. And there's ephemerons, in which you have, that's an ephemeron, so the first slot is different. It's pseudo-weak, and the rest are strong. And what happens with ephemerons is that, at least for the purposes of this talk, is that, well, when the garbage collector runs, well, since ephemerons are strong, then all of its contents are marked, so that nothing gets collected and nothing gets stomped, except the first one. And if there's nothing else other than the ephemeron itself, and yes, whatever, go read the paper, it's kind of complicated and ambiguous, but at times. But for these purposes, if nobody interesting, shall we say, references the key of the ephemeron, then the ephemeron becomes a regular strong object, and now the message mourn gets sent to the ephemeron. And the idea here is that instead of weak arrays stomping over the object that it was not in the reference, with ephemerons you still have the object that was going to be collected, and consequently you can do finalization without copying data. Great. Now, here's the problem, however. You have a gemstone installation in which you have a server full of objects, and only, of course, a portion of those are replicated or visible to clients at any which time. And these are these. Obviously, not all of them are here, because there's more there than fit here, right? So, and there is a image side client that keeps track of which server objects and client object go together. Now, how should that map be constructed? Because, of course, as soon as the application doesn't need these anymore, they will get garbage collected, and it is important to let the server know, hey, the application is no longer seeing these objects, please stop sending me notifications, please stop, telling me that, oh my god, something changed because I don't care anymore. So you could do that with ephemerons. That would be great, because each time one of these gets, it gets garbage collected, then this guy says, oh, yes, sure, well, in case of ephemerons, it wouldn't be garbage collected, but when this needs when this object is no longer referenced, this guy detects it, and with finalization, you do it one object at a time. But the problem of this is that, well, first, with each object that got copied over to the image side, you need one ephemeron per, and that's an extra object header, more slots, etc. So your memory consumption goes up. And also, finalization mechanisms are not generally designed to handle, say, a couple million ephemerons being finalized at the same time. That doesn't really work for performance considerations. So, okay, therefore, Gemstone S uses weak arrays, in which case you can amortize the storage cost by making weak arrays different sizes, and you still get all finalization behavior you want, and when finalization comes, you maybe need to mourn a few instead of mourning a lot. This is where the problems begin, because what happens with the management of weak arrays? And this is important because while ephemerons are great at finalizing one thing at a time, they impose both finalization key growth and extra storage space. And while weak arrays are great at those, because the costs are negligible, however, This means now we have to scan for tombstones, because the tombstones could be anywhere. And so, although in general, weak arrays are much more effective size-wise, they impose linear search on you. That's not fun anymore. So what to do about that? Well, the first thing that is already deployed in production and was done before I left is that at the beginning of interactions with the server, it was important that you wouldn't get unexpected tombstones at random times. And this is important because if you are effectively, I'm sure Martin can tell you more details, but if effectively you're taking a snapshot of what these tables look like, and in the middle you're getting a tombstone, now you will have to scan everything again, etc. So you don't really want that. And also, you really want to tell the server the most accurate current information, because if not, now the server will have, to keep track of this bogus information, and of course that takes time and processing and to recover from. Consequently, what to do? Well, solution one, I don't want tombstones. So let's put in a strong copy of the weak table. Now, of course, there's a strong references, and so now there's no more tombstones, so that's great. But the problem is, well, how do you, synchronize that with a high transaction throughput? Because now you're talking about copying, which takes time. You're talking about making garbage, which takes time to collect. And it's not like you can stop the garbage collector altogether, because if you're running out of memory, you will want to run the garbage collector, in which case you can get tombstones. So you can't really stop the garbage collector. And that also means, well, if before, one might be tempted to, let's say, well, but I know that I don't want tombstones anymore, so somehow magically I stop all the garbage collection facilities. Well, what happens when you really need to run the garbage collector in order to make a copy? Because there's not enough specs. So this solution doesn't really, it's not really reliable. And what we came up with, talking about this, was, well, how about the weak array becomes strong temporarily by sending it the message, is weak container false. And now the same weak array is strong. So there, no more tombstones. Right? Because obviously, if it's strong, you can't collect anything out of it. And as soon as I'm done with the thing that where I don't want tombstones anymore, I can just tell it again, well, now you can be weak again, because now it's okay for you to be weak and I don't care about tombstones right now. So this solution, which got deployed, required changes to the memory manager to deal with these strength changes. Most of the changes that were necessary were in the incremental garbage collector. Because in any stop-the-work collector, well, by the time the stop-the-work collector looks at this, it's either strong or weak. So I don't, any stop-the-work collector would not care what these changes happen. But if you have an incremental garbage collector, well, let's say the incremental garbage collector, so that this was weak, so you put it on the weak list, and now it's strong. Not really. Or how about, it marks this object when it's strong, it becomes weak, then it scans it, after it got marked, but before it got scanned, and then it scans this object while it's weak, so it marks nothing, and then this object becomes strong again, and the objects get collected right from under it. So you don't really want it. So that kind of stuff required a bunch of work to get the incremental garbage collector not to mess up anymore. And of course, that required, when you get into that, it requires changes to, well, you can do the same thing with become, we change classes, all sorts of things. So all that got fixed and that got deployed. So that's great, except that now, once you eliminate this performance problem, this one comes in. Because when you mourn a weak array, you still have to scan for tombstones. And now that all these performance problems got deleted, the next thing that turns up in the profiler is, hey, you're doing linear search. So how to get rid of that? And the idea was to observe that the garbage collector was playing hide and seek with you. You see? Because basically what the garbage collector behavior could be described as is, hey, I'm the garbage collector, I'm going to hide these tombstones somewhere, I'm going to tell you that there are, but I'm not going to tell you where. Now you go find it in the image and do linear search. How helpful? Not really. So instead of tombstoning with 0, how about tombstoning with the index of the next tombstone? You're still tombstoning with small integers just as before, except that now, by using the first instance variable, say, to record the first location of the first tombstone, well, the next tombstone will tell you where the next one is and the next one is, and now you're not doing linear search anymore. That's the key aspect of this idea, which, by the way, I have not implemented just out of lack of time, but I know from experience that it will require trivial changes to a memory manager, as described in the paper. And, well, as far as mourn goes, well, look, seriously. Look, here's your first one, which in this case will be 6. And then unless it's not 0, right? Then, well, you mourn there, so 6, 12, 15, and then you grab the next one from the next index itself. And so that variable will have the values 12, 15, 0. And when it's 0, you go here, now it's not false anymore, and you drop out, and that's it. Interestingly, I got a question from the reviewer saying, well, have you done any performance benchmarks? Well, no. I can tell you that from the VM side, the changes are so minimal to any CVM that I don't think how it could possibly be measured. However, in Smalltalk, it's interesting to make the experiment. And then I found something very interesting. Oh, one before the performance thing. Now, you could say then that if you got this to happen and you got a garbage collector interrupting you here, you might get into a situation where this weak array gets queued for mourning once, and before it actually mourns, you get another garbage collection pass that stops over all your linked list. So how do you stop that data race? Well, you stop it by having the VM adopt the ephemeron finalization convention, by which when this linked weak array is queued for finalization, the VM says, oh, and by the way, you're strong now. So no more tombstones. Magic. And then when this guy is done with mourn, it ends by sending itself, oh, I'm weak again. And so you're only weak when you can accept tombstones, and otherwise you're strong, and of course there's no data race anymore. And now you can see how the combination of all the parts. Tombstoning with weak, with small integers, and changing the strength dynamically, and of course, encoding the information so the image doesn't have to reconstruct it. Well, performance-wise, here's what I found. So, here is a graph with several columns in each cluster. Each column represents a certain power of 2 for a given linked weak array. So, for instance, this would be the empty linked array. This would be size 1, 2, 4, 8, 16, 24, etc. Right? And here is the tombstoning rate for this particular linked weak array. A tombstoning rate of 1 means every slot is tombstone. Tombstoning rate of 2 means 1 every 2 is tombstone, and so on and so on. So 3, 5, etc. And this quotient here is the ratio of performance of old weak array or traditional weak array mourning, in which you have to scan for every slot, over the performance in iterations per second of mourning of a linked weak array. So if this quotient is 1, they are just as fast. And the higher it goes, the faster the faster linked weak array mourning is. So interestingly, when everything is tombstone, linked weak array mourning with that code I showed you is 30% faster. Simply because of that code difference. You're not asking for size, you're not going to do nothing. So there, 30% faster just because. And that translates to all the others. And of course, the higher the tombstoning rate, the higher the quotient. So with a tombstoning rate of 10, eventually you get about 10 times faster. With a tombstoning rate of 7, you get a little bit over 7, and a little bit over 5, and 3, and 2, and so on. For very large linked weak arrays, this is a log plot. And you can see that indeed the performance just goes just as fine, except as you get to the larger powers of 2, in linked weak array size, the performance doesn't increase as much as in these steps, simply because now, well, these linked weak arrays fit in memory, fit in the cache, but this ones don't. So now you have to do memory reads. So that, and you can see that for a variety of tombstoning rates and sizes and everything else, and of course the quotients go up in that log plot as expected. Any questions?
Just on time.
Great, awesome. So no more questions. Well, while we change computers, I don't know if you guys want to ask something while I get out of here. For the next presenter.